Hello everyone. This is the short review of the Chapter 3 reading. The reading covered the normal curve and z-scores, and hopefully you'll see why the normal curve and z-scores are so useful to researchers after this video. The standard normal curve is shown on the graph here, on the figure here, and what makes it so useful is that it has a certain proportion of scores that fall within specific parameters of the center, of the mean. Of course, a normal curve is symmetrical, as you know, and what also makes it a normal curve is that very specific proportions of scores fall between the mean and a standard deviation step up or down, to the right or to the left. If you look at the 68, 95, 99 rule that characterizes the standard normal curve, you'll see that 68% of all of the scores in the population fall between one standard deviation below the mean and one standard deviation above the mean. So between what we will soon learn are z-scores, between a z-score of 1 and a z-score of -1, that contains 68.26% of the entire curve. 68.26% of all scores are between one standard deviation above and one standard deviation below the mean. 95.44 are between two standard deviations above and below, and then 99.72 are between three standard deviations above and below the mean. You may be wondering, well, why is this so important? Well, the reason why it's important and useful for researchers is that if you know this rule and you know how to work with these probabilities, you can take any raw score and convert it into what's called a z-score, and then determine the probability that you would get that score or something higher or lower than that score. Let me show you an example. So let's just suppose that you have a population with a mean of 10 and a standard deviation of 1. If you know the 68, 95, 99 rule, you would be able to tell that 68.26% of all scores are going to be between 9 and 11, because the standard deviation is 1 and the mean of the population was 10. So one standard deviation step down would be 9, one standard deviation step up would be 11. So that means that 68% of all possible scores are between 9 and 11. Now, if you got a score of 12, you would know, wow, I did really, really well. If you got a score of 10.5, you would still think, well, I did better than average, but you're fairly close to the mean. So you can, by knowing this rule, you can use or make some useful statements about your performance and how it compares to other people who took maybe the same test. Now, computing or making these statements is fairly easy when you're dealing with numbers like a mean of a whole number of 10 and a standard deviation of a whole number of 1. And so you can kind of do those conversions in your head, but it can get a little bit more tricky if you start getting means that aren't whole numbers and standard deviations that aren't whole numbers. And so rather than doing it in your head, you can use a z-formula, a z-score transformation. So you can convert any raw score, no matter what it is, you can convert it into a z-score. And then you can find it on this normal curve. So you get 0.5, you could locate it here, and then using a table, you could look up and see how many people had a score above or below that score, that z-score of 0.5. Again, to make this clear, you get a raw score, somewhere down here. And then, which say the mean is 10. And standard deviation 1, this would be 11. So something in here would be a score of 10.5, right? You could convert that to a z-score, and then you could make a probability statement about how many people did better or worse than that score. Stated differently, z-scores allow you to determine the percentile, or the percentage of scores that are above or below a given value. Here's a very simple example of how we can make a probability statement. So let's suppose we want to know the percentile of a z-score of +1. The first thing you want to do is draw a normal curve. So you draw the normal curve like I did up here. It's centered on 0 because a z-score of 0 is always going to be the mean in z-score language. In a z-score number line, z of 0 is always the center. And then you go up and down in 1 standard deviation steps, z-score steps. So after you draw this curve, you then want to locate the score that you're interested in, a score of +1 in this case, so it's right here. And we want to know the percentile score. So the percentile is the people who scored this value or less. So we would draw the line up and shade the area to the left. And then you have to decide whether the area that you shaded is a body or a tail. It's not that the body is always on the left and the tail is always on the right. Rather, it's the body is always the bigger of the two halves, two side pieces, chunks, proportions. So in this case, the shaded area is the body, and that's something that you need to keep in mind. So then you go to Appendix A, and you're going to find the z-score of 1 that we're interested in, because that was the value, z-score. And then you find the body probability, and that tells you that it was 0.8413. That means that 84.13% of all the people who took this test scored as well as or worse than a score of 1, a z-score of 1. Now, sometimes I'm not going to give you the z-score, and instead I'm going to give you the raw score. And so you then need to convert the raw score to a z-score. So in this example, let's say you took an exam and you earned 45 points. So your X score, your X is 45. The national average is 42.5 with a standard deviation of 2. Now compute your z-score. You can pause to see if you can figure it out. You should have found that the z-score is 1.25. The score goes in for X. The population mean goes in for mu. And the standard deviation goes in for sigma. Now we want to try and find what your percentile is. So the way you do this is you need to draw that normal curve, again, centered on 0, going up and down in steps of 1 on either side. And you want to locate 1.25 on the curve. And then you want to shade the area that you're interested in, and then use Appendix A. Go ahead and pause and see if you can figure out how to do that. Here's what your curve should have looked like. Again, it's a normal curve, standard normal curve, so the center is 0. You're going up and down in steps of 1, standard deviation, 1 z-score. You've located 1.25, which is right here. You've shaded the area because you want a percentile. You're going to shade the area to the left. So again, the shaded area is the body in this case. So you're going to go to Appendix A, find the z-score of 1.25, look under the body column, and find that it is 0.8944 is your probability. That means that 89.44% of people scored equal to or less than a score of a z-score of 1.25. Let's do a second example. In this case, you've got 25 points on your test. Your national average is 26.3 and your standard deviation is 2.8. Go ahead and press pause and try and find your z-score. You should have found your z-score to be negative 0.464. And now you want to find your percentile. What percentage or what proportion of the population did as well as or worse than that? So draw the normal curve again, centered on 0, moving up and down in steps of 1. Locate where negative 0.464 is, and then shade the target area. Is it a body or tail? Go ahead and press pause and see if you can find that, and then find the probability in Appendix A. So here's what your curve should look like. Again, a normal curve centered on 0, moving up and down in steps of 1. Now you may, you locate negative 0.464, which is right here. You may have had difficulty finding negative 0.464. It's not there. You can't find negative 0.464. What you have to do is you have to look up the absolute value of that number. So you look up 0.464. And then because the shaded area is a tail this time, you look up in the tail column rather than the body column. So the negative sign, it doesn't tell you, when you're using the table, you really ignore the negative sign. And then you just have to decide whether you're using the body or tail based on the shaded area. Now in this case, because we want a percentile score, because we wanted to know how many people scored as well as or worse, we draw the line here and then we shade in this side, and that means we're going to look up a tail. If instead I wanted to know how many people scored as well as or better than a z-score of negative 0.464, then I would want to shade this area on the right, and then I would be looking up the body. So it is important that you identify, based on the problem and what you're looking for, whether you want a body or a tail. This last problem is more challenging. So I'm going to go ahead and let you pause and see if you can figure it out. The little hint is you're going to have to use two equations here. You're going to have to, you're using the same equation twice, rather. You want to find raw scores rather than z-scores. Here's how you solve this problem. You want to know the raw scores that define the middle 60% of scores. So here's your graph. You draw a normal curve again, centered on 0, and you want to identify the raw scores that bracket the middle 60% of scores. So that means this whole curve is 100%. So that means if the middle is 60%, that means there's 20% over here, and there's 20% over here, because 20 plus 20 is 40, plus 6 plus 60 is 100. So that means this is 20% and this is 20%. The way I would always encourage people to start is to write the equation, the z-score equation, and then substitute in what you know. You're given the mu, so that goes there, 26.3. You're given the standard deviation, that goes there. X is what you're looking for, okay? And what you don't know is you want to know the raw score that starts this bracket right here. Since you know that this area of the curve is 20%, you go to the Appendix A and find in the tail column, you're using the table inside out, so you're going to find in the tail column, because this is a tail, the number that corresponds closest to 20%, or 0.200. And this is the number that's closest, so it's at 0.84. That's the z-score. So we're going to put that in for z. Now you'll notice I have negative here. Why did I do that? Because this z-score is negative. It's to the left of 0. So we're going to have to just reason it out that that's going to be negative. if I now solve this equation for x, that will give me the x score that starts the middle 60%. So you multiply both sides of this equation by 2.8, and then it brings you down here. Then you add 26.3 to both sides of the equation, and now you solve for x. This is the raw score that starts the middle 60%. Now we need to do the exact same thing for the other side of the middle 60%. So the way you're going to have to do that is use the same steps, except now the z-score you're going to be using is a positive 0.84. You could look it up again, but this area of this curve is still 20%, so you know that. An easier way to think about it is you know that a normal curve is symmetrical, and you're talking about the middle 60%. So if you drew a line straight up above through 0 there, this would be 30%, and this would be 30%. So that means this has to be 20, and this has to be 20. And since it's symmetrical, since this was negative 0.84, then this has to be positive 0.84. So again, you go through and you solve for x, multiplying both sides of the equation by 2.8, adding 26.3 to both sides of the equation, and then it gives you your x score, which is right there. So now these two raw scores bracket the middle 60% of scores in this distribution.